Hello everyone. Welcome to Network Seminar Series hosted by Center for Networked Intelligence at the ECE and RBCCPS IISc. It is my pleasure to introduce today's speaker, Dr. Jayashree Mohan, who will be speaking on scaling AI models serving QoS, multimodality and beyond. Jayashree Mohan is a senior researcher at Microsoft Research Bangalore, working primarily on building efficient AI infrastructure with a current focus on LLM serving. Prior to joining MSR, Jayashree received a PhD in computer science from the University of Texas at Austin, where her dissertation focused on optimizing storage for ML workloads. Audience is encouraged to ask questions at any point during the talk. For those attending online, questions may be asked either by unmuting and speaking directly or by typing them in the chat box from where they will be relayed to the speaker. Over to you, Dr. Jayesh.
Thank you. You can hear me well, right? Okay, awesome. So I thought today I'll talk a little bit about the deployment challenges you usually face with deploying these large language models at scale, at production scale, and I'll touch upon a few aspects of ensuring quality of service while ensuring high throughput of serving, as well as what challenges come across when we are serving multimodal models which are now emerging, actually just taking over, right? And also what are the new where is this whole LLM scenario kind of headed? What are the new advancements there and what systems challenges it brings about? So that's going to be the flavor of what I'm going to talk here. Okay. So as we all know, like LLMs have taken over almost every other avenue of life that we can think about, right? They have influenced how we interact with the search-based applications, how we program, healthcare, finance, and whatnot, everything, right? And every now and then we see advancements happening in the model space. The technology there is evolving, but underneath, you do have to deploy all of these models on a large cluster of GPUs, and you have to manage how these are being deployed efficiently, right? And that is what gives us the cost benefit or efficiency, and this has to be handled at a very large scale. So broadly speaking, our group at MSR works at all levels of the stack here in making the LLM inference much more efficient. So at the lowest level, you need to have optimized GPU kernels which run on these GPUs. This includes how do you write attention kernels in a way that's memory and compute efficient, how do you write compute kernels and so on, right? And then one level higher up, you have memory management, which is these models have to handle, you have model memory, you have their KV caches, activations, there are a lot of memories and there are plenty of requests coming in. So how do you do efficient memory management so that you can pack a lot more requests together and you can serve with a higher throughput, right? So that's another bucket, slightly higher up. And then the third bucket comes in when you have to deploy these models, say across GPUs or across nodes, then there's definitely going to be communication that happens between these, right? So how can you come up with efficient communication primitives? How can you overlap communication with compute? So all that is the next bucket. And then one layer up, you have the scheduling and the deployment decisions you make. And this has to deal with, you have now multiple requests coming in from different applications, different services. You might have different deployment regions themselves. So how do you route requests? How do you efficiently schedule them on an instance, etc.? So all these challenges are in the higher level bucket, right? And in fact, one layer above this would be applications. Like you have applications like RAGs, which would have to retrieve a lot of documents. So can you do optimizations there? You'll have agentic scenarios coming in. So those are one layer up. But in today's talk, primarily I'll kind of talk about this particular bucket, in particular two of these systems which tackle quality of service for large-scale deployments and multimodality. So in the rest of the talk, I'll give you a little bit of background about what I mean when I say deployment scenarios, what are the assumptions we are making with respect to deployments today, and then first about quality of service and then about modality-aware deployments, right? So this is something you all might be very familiar with, but still for context and terminology, I'm going to use for the rest of the talk. I'll anyway say this, right? So we have a language model or an LLM with its weight, which is on the GPUs, right? And then you give it an input prompt. What's going to happen? A forward pass over the model is going to create a representation of these inputs. Let's call that the KV cache, and then generate one output token, right? And the KV of this output token is also fed back into the cache. We keep this consistently, we keep this cache in the GPU memory. And then using this new token generated, we auto-regressively generate the next token. So we just generate tokens one by one, right? So this initial phase where we are processing this entire prompt at once is what I call the pre-fill phase, right? And then the phase where you auto-regressively generate one token after the other is the decode phase. And the primary difference between the two phases is that pre-fill is kind of compute bound because you're throwing a lot of tokens at the GPU, at the LLM, right? And all of those can be processed in parallel. So that's a compute bound operation. But the decode phase, because you're generating one token at a time, is oftentimes memory bound. So that's primarily from a systems point of view, that's primarily the difference between these two phases, right? And now this is with respect to one request coming in through a model, right? Now what happens in a large scale scenario? You have requests coming in for different sorts of applications, right? So here are just 4 different applications I've given examples of. So when all of these requests come, first you have a high level router. What this router is going to decide is you'll have multiple instances that are present, right? By instances, I mean replicas of the same model which are available because you can't handle all of the load using a single replica. So now this router will decide which of these replicas should I route this request to, right? And it could make this decision based on a lot of different things such as cache hits or maybe load balancing and a lot of other factors. But today what happens is there are typically, let's say 3 different buckets. One of them is that there will be replicas that are exclusively reserved for latency sensitive jobs where inter-token latencies or TBTs, time between tokens, is important. So you'll send all of those interactive requests to a separate set of replicas. And then you have a separate set of replicas scheduled for, reserved for batch jobs where latency may not be important but throughput is important, right? And then you'll have another set of replicas which are exclusively meant for API access or best effort jobs where you could take as much time. If there's low load, you'll get very good latency, or if there's high load, you'll get like indefinitely high latency. So typically these are like kind of siloed, as we say, right, into different buckets, and then you appropriately route these requests. And within each of these buckets, there could be different policies that figure out how to route replicas, how to route requests to these replicas. I'm not going to touch into that, but that's another challenge in itself, right, which is how can you balance load across these different replicas. And then let's say, for example, in multi-turn conversations, you could have the same prompt repeating round after round, right, for a user session. So in such cases, you'll want to maximize cache hits. So if you send to the same replicas, the prompt will be pre-filled there, so you'll get a cache hit. So you'll have to do kind of a sticky routing, but you'll also have to balance that with load. So all those challenges come across in each of these buckets. But in the context of this talk, let's talk about this high-level categorization. Today, there are these siloed deployments. Now, this kind of a siloed deployment is really good in terms of avoiding interference between these classes of jobs, right? You are separating out the latency sensitive and insensitive ones, so you know there'll be less interference. But the main challenge that this brings about is, one, the operational challenge, which is in each of these buckets, there could be a lot of load fluctuations. You'll have to do very careful capacity provisioning for each of these buckets individually, right? And that also becomes very tricky because even within a deployment, let's say we're doing latency sensitive cluster, right? Not all applications and not all requests will need the same level of interactivity, right? For example, a copilot or chat copilot you're interacting with might need a millisecond level granular responses. Whereas something like a summary that comes after, say, this meeting, right? It may not need that level of interactivity. It could come after a few minutes. We'll be okay with that. But all of these, because they're classified as interactive or user-facing jobs, they're all sent to the same cluster, right? So in some sense, there's a conflict of requirement that happens within one certain deployment. So because of that, what happens is there is less efficiency and there's less throughput because you would always optimize for the best latency in this entire bucket. So jobs that don't really need that low latency will also end up ensuring that low latency. So there's a loss of efficiency here. That's one challenge. The second one is that overload management in general is not done in a nice manner today, which is how do you manage when there's a burst of requests that's happening at a certain point in time. Today what we do is we impose, let's say, a rate limit at a user level or an application level, right? And say this application can only issue X requests per second, right? Or this user can only issue X requests per second. Or we impose other kind of restrictions such as, when there's an overload, I'll prioritize only all the short requests in the system. I'll just end up dropping all the long requests because they'll block all the small ones for me, right? So these kind of schemes are not really fair, one. and also they are not aware of the importance of the job, right? So I cannot always drop a long job because that long job could be issued by a user who is like in a, in a very highly paid tier, right? And all the short jobs could be coming from a free tier, which we are prioritizing over this one. So without really knowing what application is sending it and how important that request is, any kind of this overload management technique is going to be not so fair. So that's the second problem with this kind of deployment, right? So as I said, in this context, like one aspect we are considering is cost efficiency. How can you make the deployments much more efficient in terms of cost and resource usage? But at the same time, how can you ensure quality of service? Because by doing that, you should also not affect the TBT, like SLOs that these latency sensitive jobs need. So how do you balance both? That is the primary question that this first work Niyama tries to address, right? Which is how can we achieve high throughput while also meeting quality of service constraints under practical fluctuating load scenarios, right? That's the high level problem formulation. And the key idea that we're using here is, one, we can define SLOs for different categories of jobs, and these SLOs can be coarsely defined, unlike other, big data jobs or otherwise, where defining SLOs itself is very hard. But unlike that, in this scenario, it is relatively easier to define SLOs. So we can define SLOs, and once we do that, we could do a lot in terms of scheduling them in an SLO or in a deadline aware fashion. So that's the first idea. And the second is we could do overload management using application hints and schemes like hybrid prioritization. I'll talk about both of these in a bit more detail. Right? And using these techniques, what we could do is serve about 20% higher throughput or 20% higher capacity in a cluster without compromising on the quality of service. And at times of load fluctuations, we could reduce the number of deadline violations or the request violating deadlines by almost an order of magnitude. So that's a high level takeaway from this work. So I'll talk a little bit more about the details and the results. Also feel free to interrupt if you have any questions. Yeah. Yes, there is. There is a trade-off, which is if you try to optimize throughput a lot, then you could end up hurting meeting the latency SLOs of some requests. So you can optimize throughput only as long as the SLOs are met. There is a trade-off to be made there, yes. So the QoS umbrella is that, I'll maybe talk about it, probably in just the next slide, yeah, what QoS means. Okay. So that naturally transitions to the first question, right? What is really QoS and how do we define it? So the prefill and decode phases that I talked about, right? Like every prompt is going to do a prefill and then auto-regressively it's going to do a bunch of decodes. Now what do we care about when we say quality of service is that the time to first token, which is when does prefill end and when do you see the first interactive token that's coming from the application, right? So users care about that, or users or some applications care about that. That's called TTFT, or time to first token. And then there's another metric called TBT, or time between tokens, which is the inter-token latency, right? How interactive are the subsequent tokens from the system. And then there's also this other metric called time to last token, which is when you get the entire output, right? Not all of these metrics are equally important for every application, right? Let's take, for example, if you're talking about Copilot or use chatbots, right? So there TTFT is important because you care about when you get the first output token, because that improves engagement with the user, and you also care about how often a new token comes because it has to kind of match with your reading speed. Otherwise you'd be bored, you'd kind of wander off, right? So for those kind of applications, both a strict TBT and a TTFT matter, and we can set certain limits. Like TTFT is typically set in the order of few seconds, like 1 or 2 seconds maybe, and TBT would be in the order of a few tens of milliseconds. 25 to 50 milliseconds is typically what most production scenarios use, right? So those could be important for copilots. So another case could be like summarization that happens after the meeting, this meeting, right? So there TTFT and TBT may not be important. All you care about would be TTLT. When do you get the summary, right? And we could define that maybe in the order of a few minutes, right? Like it could be like 2 minutes or 3 minutes. That should be reasonably fine time to get an output token. And then the other thing you could have is, for example, if you're using Outlook for emails, right? You would get, at the end of the day, you might get a summary of these are the emails you received over the day. Here's an insight for you, right? So those could be happening in order of hours, right? You could have it like once a day or something like that. So depending on the applications, it's easy to set one of these metrics, one or a couple of these metrics, and that defines what quality of service means for the application. So that's how we are defining QoS in the context of this work, right? So now that you have defined QoS, the key idea here is that previously for each of these applications with different QoS, we had deployed a different siloed cluster, right? So the key insight here is that now you don't need a siloed deployment, rather just use a single shared cluster and schedule all these jobs now which are tagged with SLOs in the same shared cluster. And then now comes the challenge of now how do you schedule jobs each with a different SLO, each targeting a different SLO metric, and how do you ensure that they all meet their SLO targets, and how do you do this on a shared cluster? So that becomes the major scheduling problem that we have to tackle here, right? And the insight as to why this would be better than doing a siloed cluster is that now when we are co-scheduling jobs on the same shared cluster, there could be one job which finished a bit earlier, so it would have accumulated a slack with respect to its deadline, right? Its deadline is its SLO. So now we could use this slack to schedule another job whose deadline is the earliest from now. So jobs keep accumulating slacks, and these slacks could be used to kind of schedule the other pending jobs in the system. So that way you will make the most use of the available throughput in the system. So that's the high level insight. And how we do this, I'll just talk about in the next couple of slides. But is there a question so far? Yes. Mm-hmm. I think it will become clear when I have a flow diagram that shows how the scheduling happens. It doesn't happen upfront. As in, requests come in, they sit in a queue, right? And then when it's time to schedule the prefill of the request or the decode of the request, that's when you see whether they have met their deadlines, whether they have met their TTFT or TBT deadlines, and you decide which next request to run. So it happens at the granularity of, you can say, iterations or batches. No, we don't assume that. They do not have actually. So what is it makes this app similar, except with the queues directly? Yes, yes. So it could be the case that an interactive job that needs a 2-second latency could be of length 1000 or could be of length 10,000. So, but you assume at least stationarity in terms of the distribution is the same. It is coming from the distribution. That is also not. No, not necessarily same. It could vary. True, it is the same app, but it depends very heavily on the user as to what the characteristics of the requests are, right? Like when we are interacting with a chatbot, like the length of queries you send could be very different from the length of queries I send. So that way, but one thing could be similar, which is I do agree that the decode length distribution is more or less, you could say they are from the same distribution. The user prompt can vary very widely, but the decode length or the number of output tokens it generates is kind of application dependent. Yeah. Yes. I'll maybe explain this and I'll take any more questions. So just as we get into the scheduling phase to talk about what better we do in terms of scheduling, I wanted to bring up the difference between the prefill decode and introduce chunk prefill in this context, right? So what this graph here is showing is as you're increasing the batch size, which is the number of requests that are scheduled in a batch, what happens to the latency of prefill versus decode, right? That's the graph on the left and the right. So what you notice here is on the left, as you increase the batch size, the latency of the per token latency of prefill almost remains the same, right? Whereas on the decode, if you see, as you increase the batch size, what you're seeing is that your latency drops significantly, which means prefill benefits by doing a much larger batch size, which is you're gaining in terms of throughput as you increase batch size for decodes, not for prefills, right? Which is prefill is a very compute bound task, whereas decode is not. That's kind of what the high level takeaway is. And the other observation is if you look at the absolute scale of the y-axis itself, right? decodes are up to like orders of magnitude much more expensive than a prefill, because you're decoding one token, you have to process all the KVs that have accumulated so far in order to decode that one token, right? So they are much more expensive. So it's always beneficial to do decodes in much larger batch sizes and prefills in really small batch sizes, because you're saturating your throughput even at a batch size 1, as long as you have a reasonably sized prompt, right? So that's the high level takeaway. So yeah, yes.
What do you mean by batch size in prefill? I mean, I could just take if my input prompt is pretty big, right? I mean, I can the whole one prefill itself might
Yes.
just saturate
Yes.
my relegation.
Correct. Correct, correct. So for this particular graph, the prefill batch size was computed assuming that every request has around 4,000 prefill tokens, right? So at that length, even one single request will saturate your compute. But then you can assume, like when I get to multimodality, I'll tell you, the prefill lengths there can be as small as 50 tokens or 100 tokens. So in that sense, batching would help prefills. But typically in these...
The parallel is fine. You're saying if your parallel computation has like, is your parallel computation capability is much more than what you're using in your one prefill, then you can use the batching to improve it. Right?
Yes. Yeah. But typically for most applications, like a batch size of 1 works perfectly fine, because there are system prompts that are thousands of tokens long. So typically a batch size of 1 works for prefill. Right? So given this, how does scheduling... Yeah, go ahead. No problem.
In the typical, what is the typical batch size you do to take it for decode in practice, in the kind of application you're looking at?
It varies widely. For the small scale deployments, which is for models that are not deployed across a lot of GPUs, your decode batch sizes could be in the order of a few tens. Whereas like if you see the DeepSeek kind of deployments where they used 72 or 100 GPUs to deploy a single model, right? In those deployments, the decode batch size go up to 256.
But this is really a cluster, but per GPU really a batch size much smaller, right? Per GPU.
Yes, per GPU the batch size.
That's what I want to understand. So even because we don't have H100s and 100. So what is the typical batch size for a single GPU you would use for decode? That's what I want to understand.
For a single GPU, like if you're deploying a Llama 8 billion model on a single, I don't have numbers, like I think it's the A6000 GPU roughly, I think it will be like 40 to 50 is an achievable number. Yes, yes. Is this limited by memory?
No, you don't have enough to store.
Yes. And this will depend on the sequence length or the prompt length of the request too. Yeah. Right. So given this context, how does scheduling actually happen today? So let's say there are two requests, A and B, which are in their decode phase currently, right? And then when two new requests come, C and D, we have two options here. One is you could do the prefill of the request C and D, and then continue now with a larger batch, like batch size 4 of A, B, C, D, which are all in their decode phases, right? And as I said before, increasing the decode batches is beneficial. So this kind of scheme is going to be beneficial in terms of throughput, because it's maximizing the decode batch size. But the main problem here is that decodes are going to be stalled, right? Ongoing decodes, you're going to pause them until the prefills in the system are going to finish. So there'll be a huge stall in decodes that you see. And we talked about TBTs, inter-token latencies, right? That's going to be affected in this kind of a scheme. So another alternate option is keep going with the decodes that are already present in the system, finish off all the decodes, and then schedule any new incoming prefills, right? And this is really bad for throughput, because your decode batch size could keep progressively dropping, so you're not utilizing all the compute that's available in the system. So this is bad in terms of throughput, although it could be great for latency, right? So is there an intermediate somewhere between the two, which is, can you not pause the ongoing decodes, but at the same time also do some of the prefill computations in parallel, right? So that was the whole idea behind Sarathi or chunked prefills. And the key idea in Sarathi or chunk prefills is, let's say here there are 5 different requests, right? The solid are the prefill parts of the request, and then the dotted ones are the corresponding decodes. Now, if there are 5 requests, what would a scheme like Sarathi do? You would initially do the warm-up phase, you'll do some prefill, but once you have enough requests in the system, you decide on a chunk size, which is the number of tokens you'll process in a batch. And all of the decodes that are currently running in the system, you'll first schedule them. Okay, let's say the chunk size is 1K. And you have 10 decodes ongoing in the system. So you'll put in all 10 decodes, and then 1K minus 10, that many number of prefill tokens you'll pick up from a pending prefill request. And then now you'll create a batch of size 1K tokens, right? And the prefill and the decodes are executed in a combined fashion in a batch, and Sarathi has techniques here to fuse the MLP computations of the prefill and the decode stage request. So you can assume that the decodes MLP are almost coming for free because they are kind of piggybacking with the prefill MLP. That's the high level idea with Sarathi. So you basically do fixed size chunks. Yes. You can think of it either both ways, right, in Sarathi. So if you have a very small batch size of decodes, you can assume that the decode MLPs, let's say an MLP of size 20 is going to be completely memory bound if you execute it independently. Versus if you piggyback it with an MLP of size already 1000, you're going to get those 20 decodes for free. That's one way to think about it. The other way is, let's say there's a decode batch size of maybe 256 or maybe 240, right? And if you piggyback a few prefill tokens with that, you'll get the prefill MLPs for free if you're doing a chunk size of 256, for instance. So you can think of it both way. But the essence is that one of these is usually running with a really small MLP, so you're fusing them to make the MLPs more compute efficient. And that is the benefit you will get when you're running with Sarathi. So as you pointed out, it may not be beneficial in all kinds of scenarios. In scenarios like this where you're running a small MLP, that's where this kind of a fusion would help more. Yes, it would. What do you mean by fuse it? Uh-huh. It could be if MLP is not the major component in your batch time, but rather it's the attention. Right? Yes. No, in this example they don't, and I'll come to the point where they'll start missing their SLOs. Yes. Not really, not really. That's not how continuous batching works. So as soon as requests come in the system, assuming like the system is starting from scratch, right? You will just do prefills, and as long as there are decodes in the system, even if it's one decode, you do this, you start doing this piggybacking. One decode will start piggybacking with the subsequent prefills, right? You don't wait until you accumulate a certain batch size, right? Okay, so we'll keep going, right? And how do we pick this is also a question, and we do this based on a hardware model, a combination of those factors. Because if you pick a larger chunk size, as you can see in this graph, the red line, the throughput would be higher, but it also comes with an associated high latency. So typically what we do is we look at the TBT that we have to meet, and we pick a chunk size such that if you're processing that chunk of tokens, it falls within that TBT range. The batch time should be typically less than the TBT. That's how we end up picking a chunk size, right? So let's see, like, how does Sarathi kind of perform with SLO awareness now that you have requests with different SLOs and you're kind of co-scheduling them on the same cluster, right? So these same 5 requests, now let's tag them with different SLOs. So the first 2 requests are tagged with an SLO of 6000 seconds. The second one is an interactive job. So it has both TTFT as well as TBT. And the third set of jobs have only TTLT, like they are 600 seconds, right? Like hour, second and minute granularity. There are 3 categories of jobs that are coming in. And let's say they are all coming in at this in times shown here. And on the bottom, I've marked the deadlines of these jobs relative to each other based on these numbers, right? On the x-axis here. Now what Sarathi would do is, whichever request arrived first, it's going to do the prefill of that. And once a prefill is completed, it enters the decode stage, you're going to do this chunking, right, based on a certain chunk size. And then it's going to keep doing this get new requests in order of their arrival to their prefills and decode, right? This is what standard Sarathi chunking does. But if you notice, what happens is a lot of these requests will probably finish much later than when their deadline was supposed to be, because there is no deadline awareness in the scheme whatsoever, right? You're not looking at the deadline of the jobs at all when you're doing the scheduling. So what this could mean is most of these jobs will miss their TBTs, they'll miss their TTLT deadlines because you did nothing to ensure them. So what we do in Niyama to kind of address this, yeah, so there are 2 problems, right? One is they're unaware of these differences in deadline, and we're treating all of the applications alike. So what we do in Niyama is twofold. One is, because now we have tagged them with SLOs, we know when their deadlines are, and you could do a deadline aware scheduling. You could do something like earliest deadline first, right? So that's the first idea. So instead of scheduling jobs in the arrival order, You do them based on their deadlines. So let's say we picked a different job now because its deadline was the earliest, right? And now what you could do is, see, because this blue job here has finished much earlier than its TTFT deadline, right? And this is where the first output token or the TBT is expected, right? Which means it has accumulated so much slack. It need not produce its next output token until this point in time. So then what we could do is, instead of scheduling a fixed chunk size, we could extend the chunk size. We could schedule a much larger chunk. So you get a much better throughput here. You could throw in all of the other pending prefills here to execute a much larger batch of requests, basically, right? So this is called dynamic chunking. So you dynamically increase the chunk size, but at the same time you're doing this in a deadline aware manner because you know when the next output token is expected, right? But once you get the first output token of blue, you know that this is an interactive job. You have to meet the 50 millisecond TBTs. So the next chunk you cannot violate, right? You have to fit it within the 50 milliseconds. So you do the same smaller chunk. And you keep doing this until the blue job finishes its decodes. But now at this point, there is no other job in the system which needs a 50 millisecond latency. So you know that you can extend the chunk size again. You could probably schedule a much larger chunk size again. And these kind of larger chunks will help you improve the throughput of the system. And because we are looking at the deadlines when we are doing this, we can do this in a deadline aware manner. So that's the high level idea of dynamic chunking that Niyama uses. Yeah. So you can think of this as being attached to every request. So you can think of it as something like a header. So this is just an additional parameter that we define with every request, as like how every input request has a prompt length, right? And a number of expected, not really expected tokens, that is undecided. But similar to a prompt length, we define another parameter that says this is its SLO. This is its TTFT, TBT or TTLT, whichever field is applicable. Yes, no. So if there is a decode in the system, it will be executed. We don't hold it off. The only scheduling we do is that because it can be piggybacked with a larger chunk, it could be delayed. It may not be the same small TBT, but we don't hold off the decodes. And it was a conscious choice because to hold off a decode, you might be memory capacity bound in many cases. So you'll have to move this KV cache out, right, in order to bring more prefills in. And that is expensive to do for a decode, because in a few milliseconds you might want to bring all of that KV cache in when you decide you need to execute the next decode, and that is an expensive task to do. So we do preemptions only in the prefill phase.
So here once the prompts that are already in the KV cache, they don't have differentiation.
Yes.
Exactly the same.
Yes, that is true.
What if your vehicle range is so fast that you cannot store in KV cache? That means, so suppose the KV cache can do 40 cores together, right? For 41st prefill. What do you do?
We don't do the 41st prefill.
That means you just stop.
Yes. Yes. So in experiments, how we evaluate this is, for the trace that we are running, we have to figure out how many replicas you need to deploy to manage this load, right? So we kind of do a per replica, what is the max load you can reach for this given trace. So we do take this into consideration, that we define load as the point where your TTFT SLOs, P99 of your TTFT SLOs don't go beyond a certain point. So this is a lot of, brute force search you do have to do in order to come up with that load number. But we do ensure that such situations don't happen. You're not queuing up prefills.
Once you have decided your chunk size for allocated for prefill, does that change dynamically or?
So the chunk size we decide, the baseline chunk size is decided for the lowest TBT you have to meet. From there, the expansion and shrinking of the chunk size happens dynamically, like on the fly, based on a model that we built using a simulator we have called Vidur. So using that simulator, we profiled for different chunk sizes what is the latency, and then we do a back inference on, if I'm given this latency, what is the chunk size I can fit for this model. So we do this on the fly. Right? On the fly, you know what are the requests at hand now that I need to execute, and what is the slack I've accumulated so far. So how much can I take for the next batch? This is information I have on the fly at schedule time. It's not a table lookup. Currently, it's a random forest model. It's not as simple as a table lookup. It's slightly more nuanced because of the attention and other things that come into picture there. But input parameter basically you can think of as latency, the sequence length or the current prompt lengths of all of the requests that are there, and the batch size of decodes, because that determines your decode attention time. So using these parameters, we can back infer as to how many prefill tokens we can put in. Yes, yes, correct. Yeah, it's as good as that. Yeah. So right now what it is doing is, it is trying to meet the SLO of all of the requests which are currently in the system or which are currently running in the system. Mm-hmm. 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 Correct, but if the new request that's coming in is a part of this particular replica, then you will take that into account when you are planning to schedule on this replica. But you don't take into account a future request which has not yet started executing. You would not consider what would happen to that. I'm thinking that you'll need to do at a slightly higher, like routing level, right? Like if a new request is coming in, you might want to see which of the replicas has lower load, where do I have the highest potential of meeting my TBT if I send it. This is slightly at a lower level. Ha, true. I get your point. Yes, yes. So this is looking at a single request by request level. It's not looking at the end-to-end TTFT of, let's say, multiple rounds, or in an application if you're triggering multiple agents, right? What is the end-to-end latency? It's not looking at that. That's actually some ongoing work in our group, but this, in the context of this work, no, individual requests. Yeah. Right? So that's with how we meet the SLO targets using an SLO-aware scheduling, right? And the next thing, I'm not going to talk much about it, is load fluctuations. So load fluctuations are going to be super common. What this graph is showing is at the granularity of days, but if you kind of zoom in, right, this is rolling average over days. I can't show you the internal traces, but if you look at it, there's a lot of load fluctuation even at like a minute granularity, you can say, right? Loads go high and up. And if we usually provision for the peak, then all the other times it's going to be underloaded. So let's say we kind of provision for the average, and you know that there are going to be peaks going higher than that at any point in time. This could be because of, you know, new users being added. There could be like transient failures that are happening to some of the nodes. Any of these reasons could result in these spikes, right? And what happens today when such spikes happen? So what this graph is showing us, as you increase the load on the x-axis, what happens to the latency that a request sees as the load increases in the system, right? And what you see here is, let's say the operating point of this particular model GPU combination is somewhere around 3 queries per second. That's the load it can usually handle, right? When the moment the load goes even 20% higher than this, what you'll see is that all the requests in the system, right? This is like the median, this is the P99 latency across all of the requests, like the orange line, right? All of the requests will start seeing orders of magnitude higher latency, which is essentially like denial of service, right? You send a request, you never get back a response. That's what happens when load increases in the system. And why does this happen? Because we typically use, what do you say, based on arrival time. We basically schedule these requests based in the order in which they arrive at the system, right? And as more requests come in, the queuing delay is going to kick in, and the queuing delay is going to just exponentially increase for all of the requests in the system. Yes, yes, absolutely. That's as simple as that, right? So we know that this kind of scheme is going to break down in terms of median latency itself. All the requests in the system are going to face an increased delay, right? So an alternative scheme that most people have in practice is that you prioritize short requests, kind of drop the long requests which are hogging the queue and prioritize the short ones. So this scheme, as you can see, is really good in maintaining the median, right? Like 50 percentile of the requests in the system are not going to see a latency spike. But then the problem here is the tail starts increasing much faster. That's because you're deprioritizing all the long requests in the system, and you're doing this even when there's not really high load. You'll start deprioritizing all the long requests. So this is not really fair in terms of how it is prioritizing the request, right? So is there a middle ground between these two when it comes to overload management? That's one of the first ideas with respect to overload management. And one of the key ideas here was, instead of prioritizing strictly based on arrival time or strictly based on the length of the request, which is the prefill length, the length that we know of, can you do somewhere in between? Like, can you use a combination of the two in order to prioritize a request, right? And it turns out that you could do that, and you could do this dynamically based on the distribution of the requests in the system too. So here is the constant that shows you how much importance you pay to the prefill length and how much importance you pay to the arrival duration, right? And if this constant is kind of zero, it's FCFS, where you pay importance only to the arrival time. And if the constant is like infinite, it's basically something like SRPF, or where you prioritize the short jobs. So depending on the workload, what you can do is come up with like a middle ground here, which will have medians as kind of close to that of the shortest job first kind of scenarios, but it'll also have tails which is kind of closer to that of FCFS like scenarios. And this constant, to pick it, you have to kind of dynamically, what we do is we do a piecewise scaling of this constant based on the load, and see when it is kind of closer to both of these extremes. So this is like one idea we have with respect to load management. But the other more important idea which helps us handle load better is, despite all of these optimizations, when load goes beyond 20-30% of what you have provisioned, systems are bound to break down no matter how much of these heuristics you play around with. And when a system breaks down, it is better to eagerly relegate or delay a few of the requests at the peak rather than letting all of them getting affected. So that's a more practical approach to do, which we do. So what I'm showing here again is, with all of these optimizations in place, throughput optimizations and hybrid prioritization, despite that, when load increases, your latency goes up by orders of magnitude, right? But with eager relegation, which is what you could do is, you can relegate maybe 2% of the requests, right? You eagerly relegate them, which is, you look at requests that are most bound to miss their latency SLOs, right? Which are closer to SLOs, you know that even if they run the next batch, they're going to miss it anyway. In such cases, you don't execute them, you eagerly them, or you eagerly relegate them to a low priority queue, so that if there is spare capacity available at some point, they'll run. But for interactive jobs, you can assume it's as good as just dropping them. So just by dropping 2% of the requests in the system, you could sustain the median latency of all of the other requests much better, right? So at this load, which is almost 2x that of the provisioned capacity, the baseline systems will have like thousands of seconds of latency, like orders of magnitude higher. But by dropping just 5% of the request, you could sustain the median latency for the 95% of the requests in the system. No, you can drop them at any point in time. In the middle of the prefill, in the middle of some of the decode iterations. So wasted work. Yes. No, we don't do that. We don't do that. Yes. Yeah, we don't see how close the request is to completion when we decide to drop them. Yeah, but practically it becomes difficult to have these kind of prediction systems in place, and at times of overload, a more simpler but fairer scheme is what works better in production scenarios. Yeah. Yeah, correct. Auto scaling is in effect, but then auto scaling in this context also comes with a high startup overhead, right? You have to load the model weight, so you can assume anywhere between like maybe 5 to 10 minutes of overhead in starting up a new instance. So you can think of these schemes.
Some initial computation has to be done, it will take time.
Yeah. But model whales also, right, you don't have spare GPUs all the time. One, it's also very difficult even if you have provision to get a GPU at that instant.
Charge higher.
Yeah.
When you say longer requests, on what basis do you decide?
Prefill.
Only
Only prefill, yes, yes. Because that's all we know about. Decode lengths are unpredictable.
But once the prefill is complete, then you have no.
Once
No,
the,
you stay in the system. Decode is happening, but still not you. Your SLO is passed out, you're expired. Then you say,
Yeah.
let me drop it and then you say you don't add anything.
yeah, yeah. Okay. In the interest of time, I'll keep going. So this is how the overall design of Niyama looks like. We have applications now that are tagged with different QoS metrics that come into the system, and they go into a prefill queue from where they are picked, from where you select which of these prefills would you now prioritize to run in the next round, right? And then you check with a verifier here, which is to see whether you need to run this prefill, whether you need to run this request in the current batch or should it be relegated. You know, does the load allow it to kind of meet its SLO? And then for the given batch, you put in all the ongoing decodes, the chosen prefills, you use a chunk size estimator to figure out how many of these prefills you need to put in, and then execute this batch on the GPU. And this happens every iteration. And a few results, I'll not go into a lot of detail. We evaluated this on a 16 GPU cluster across different models, different workload traces, and different combinations of these three workload categories like second granularity, minute, and hour granularity traces. And one of the main results is like this is results across 16800 GPUs. The siloed deployment with three different workload categories, right? Interactive job, minute granularity, and hour granularity job. When we did a siloed deployment on one of these traces, it needed 7, 3, and 3 GPUs each. Each of these clusters needed them to meet the SLOs of each of these individual tiers with no violations, right? And with Niyama, we could achieve all of these SLOs, but with just 10 of these GPUs instead of 13, which is like 23% fewer GPUs. But also what would happen if you ran the silo with the same number of 10 GPUs, let's say you had access to only 10 GPUs, right? Then the siloed setup would end up violating 60.4% of the jobs in the system. And it also violates them by a huge margin, not by some really small amount, right? Like this is the SLO 6 seconds, and you see a median of like 11 seconds here, and 600 to 4,000. So it kind of violates by a huge margin, right? And I'll kind of skip this, but this is another interesting workload. So assume that the workload is very bursty, right? It goes between highs and lows. In such scenarios, what this is showing is an FCFS-like scheme versus you could also argue that EDF is not something new. So once you have SLOs, you could just do an EDF-based scheduling without even using any of the ideas in Niyama, right? So in that case, this is the blue line that shows what happens if you do an EDF-based scheduling. And both of these kind of break down whenever bursts happen, right? The EDF kind of sustained 2 bursts, but beyond that, again, queuing delay shot up and it cannot sustain the latency. Whereas mainly because of eager relegation, Niyama can control the median and the P99 latencies within the bound. And to be able to achieve this, Niyama ended up relegating 8% of the requests at most. Yes. No, actually I don't have it here, but I also have SARPI SRPF, which is, it say violates the longest 8% of the jobs, for instance, right? So that also doesn't do as good as this, it doesn't sustain the load. The throughput reduction. It will translate to the number of tokens in those 8% requests. So you could say the wasted effort was not huge. So this is something that we empirically saw, that the wasted effort was in the order of, you could say, like 1 or 2% of the total fraction of time spent in doing the other requests, because we ended up mostly relegating requests in their prefill phase. Those were not requests that did a lot of decodes and then you end up relegating them. Most of the requests you would figure out that they'll violate right before they meet their TTFTs.
It would also be dependent on your workload nature. So if
Yeah.
your workloads are
Not necessarily. It could be like after a couple of prefill chunks are done, but before the full prefill is completed. It could be dropped at that point too. Yeah. Yeah, and the choice could also be the request that is still waiting in the queue. You know that there are 2 other requests ahead of me which are going to go in, and I am not going to be able to meet my deadline anyway. You'd miss that. Yeah.
That to happen even before you went to
before you went to prefill phase. Yes, yes,
waiting for 10 milliseconds after.
yes. Yeah, that could also happen. Yeah, yeah. Okay. So I'll just move over a bit quickly to multimodality and what new challenges this brings about, right? So far we talked about text-only requests, where the typical flow is like you do tokenization of the text and you pass it through the LLM. But what does multimodality bring something new to the table, right? One is, let's say for example, you have images. The same applies for audios as well. What you have to do is you have to do a pre-processing of the images. This could be cropping the images, like resizing them, etc. The standard image processing stuff, and then you pass it through an image encoder which will convert the image tiles, which will take tiles of the image and convert them into tokens or embedding. Okay, and then you project all of these embeddings to the same dimension that the LLM takes the text embedding space in. So you make sure that the embedding spaces are the same. Okay, and then on the other hand, in parallel, the text tokenization would have also happened, and now these image tokens and the text tokens are passed together to the LLM backend. And how these are passed together, there are different ways in which different models handle. Also, like this is what you get as a text output, and then if you need image output like what DALL-E does, you pass this through a diffusion model to get a multimodal output as well. But we'll focus only up to this point where you get the text output. No, this is a text related to the image that accompanies the image. So here there is a step which I have not showed after the adapter that makes sure that they are in the same vocab, they're in the same space. Yeah, yeah. So and the way these image tokens and text tokens are combined at the LLM head is different for different architectures of multimodal models. So there are 2 primary architectures. One is called the decoder only model, which is you take the same pre-trained model that you have like the Llama or the Qwen model, right? And then what you do is just append the image tokens that you've generated from the images to the text that accompanies it. Simple, right? So if you have more images, your input size is also going to be very large for the LLM. That's the decoder only model, a very simple architecture. The other architecture which optimizes for efficiency, here as you can see, if the larger the images or if you have a video, right, your prompt length is going to be super huge and the LLM is going to take a lot of time to process it. So an alternate architecture is cross attention, where all these image tokens that you have come up with, they are not going to go through all the layers of the LLM. Instead, there are specialized layers called cross attention layers, where the text tokens will attend to the image tokens. And these cross attention layers don't happen in every layer. They'll happen once in every 4 layers or 5 layers. So there are fewer cross attention layers in the model. So this kind of architecture optimizes more for efficiency, but in terms of accuracy, they don't come close to the decoder only models. So what we're seeing is more and more the models are decoder only because of the accuracy that they can give, right? But in this context, how does serving happen today for multimodal models, right? Today they are deployed as monoliths. And what do I mean by monolith is that now you have a bunch of these image related components, right? You have the encoder, the pre-processing unit, and then you have the LLM head. So all of this is packaged and seen as one unit, and then you deploy it on the GPU using the same batching strategies, the same parallelism strategies for all of these modules alike. So that's what today's monolithic deployment does. And one of the first things we did is take a bunch of these different kinds of models that are available today and do a characterization study on how this kind of a monolithic deployment affects or what systems implications does this have, right? And a few of the important observations is that one, if you look at parallelism, right, you're increasing the parallelism degree here and you're looking at what happens to the encoding latency and the LLM head latency as you do that, right? And what you see is the encoding latency does drop to a certain point. But beyond that, the encoding latency actually increases as you increase the TP parallelism, because the encoders are really small. You can think of it as a few 100 million parameters, unlike LLMs, which are few 100 billion parameters, right? So splitting them too small is not going to be beneficial, whereas the LLM head does benefit from going to TP8, right? So that means the same parallelism strategy may not work for both the encoder as well as the LLM head. They need to be kind of different. And the same applies to batching strategies as well. So these are lines showing for different models, but let's take one line as an example. So encoder means the image encoder, which is going to take tiles of images and convert them into tokens. You can do it separately for the two. Yeah, LLM head is a regular LLM that we are aware of. So even when it comes to batching, right, what you see is here image encoding, the gray line is what shows linear scaling. As you increase the batch size, how your latency scales, right? So the blue line is close to linear scaling, which means image encoding is kind of saturating throughput right here, right? But here if you see, as you increase the batch size, you'll see that the latency is not really increasing, which means it could probably do a much bigger batch size. And this is like the Llama 11 billion model, which is the cross attention based model where your input size doesn't increase with the number of images, right? So your texts are very, very small. So that could benefit from batching, whereas the images are not benefiting from batching. So essentially high level point is batching strategies and parallelism strategies. The optimal ones could be very different for encoding and the LLM head. And the other observation is that if you look at the time spent in image pre-processing, image encoding, and the actual prefill of that entire prompt, right? We observe that for many models, encoding takes up a lot of time when compared to the actual prefill, right? Almost 80% of the TTFT. And these are CDFs that show it. Basically, the orange one is the image encoding time, right? If it's closer to the gray line, that means that's the most dominant part of the TTFT for many of these models. So encoding is taking up a lot of time, so we need to do something to optimize image encoding time if we want to optimize for TTFT. That's the other takeaway. And the other observation from some of the production traces was that this is a trace that shows for different periods of time what is the number of images per minute arriving in the system and the requests per minute for an associated trace. This is for the same trace, right? And what you see is that there are modality specific bursts here, which is the queries per minute is more or less kind of constant in this range of time, right? But if you see, there is a huge spike in the number of images that come in with these requests, similarly at a different point in time. So the text load could be kind of uniform, but the load at the image encoders could vary very significantly. So there's modality specific bursts that could happen, all right? And these two bursts may not really align at the same time. So you need to do a lot of these things modality specifically. So the key idea in ModServe is that because the scales, because the different stages scale very differently, you could decouple these stages of image encoding and the LLM head operations, and you could do auto scaling and optimizations independently for the two stages. So that's one key idea. The second one is how do we eliminate the image encoding bottleneck, right? A very simple observation here is that as you have more number of images, the encoding of these images are not tied to one another. This is just embarrassingly parallel. So you could just spin up more encoders and do this encoding in a parallel fashion if there is a burst or a load in terms of how many encoding you need to do at a certain point in time, right? So we could do that to optimize for TTFT. And the other one is modality specific bursts. How do you handle it? We need to do the routing and the load balancing strategies in a modality specific manner, right? And also do auto scaling in a modality specific manner. So scale that, auto scaling that reacts to these bursts. Yes. Not necessarily different, but that would be dominated, I think, for the decoder only model and the cross attention model you're talking about, right? For the two architectures. Yeah, encoding phase is terribly compute bound. You can think of it as a prefill, similar to a prefill. So it's going to take, yeah, it's just matrix multiplication. It's just matmulls. It's going to take a tile of images, different pixels, and it's going to do matmulls over it. It is just doing a bunch of MLPs, yeah. Yes, yes, yes. Yes. So there are different encoders that use different techniques to do it, but at the essence, it's all compute bound. So encoders are heavily compute bound.
And for these, you cannot use those shaders or
I am not aware. What do you mean by?
the GPUs also have this shaders and the graphics.
I see. No, as far as I know, all of these are still using the tensor cores. They are accelerated by the tensor cores, these operations too. Yeah. Yeah, that's my understanding. Yeah. Yeah. So the key idea in ModServe is that you can have a bunch of image nodes which have the encoders loaded into them, and then a bunch of text nodes which host the LLMs, right? And then the image nodes independently do the image encoding part, and the text nodes do the LLM head part, and then whatever you have encoded, the image tokens, you can transfer via RDMA to the other set of nodes. That's the very high level design. But we also experimented with what happens if you don't have specialized networks like RDMA, if you have to do TCP transfers. But even then, this kind of an architecture is better than doing the monolithic coupled architecture. I think I'm kind of over time. Like, is it okay if I take 5 more minutes? Okay. Okay. So I'll not go into a lot of detail of ModServe, but so we have an image pool, right, which are basically you can think of as instances of the encoder, and then we have a text pool which is just instances of the LLM, right? And when a request comes in, what happens is that if it's a text only request, not all requests will have images, right? If it's a text only request, you send it to a text router, and the router will figure out which of the text replicas I need to send this to. The same as what we saw in Niyama. A router decides which one to send this to, right? But if there is an image, then an image router comes into picture, which will decide based on the load at these different image instances, where should I route the images in this particular request to, right? And a single request could have 100 of images, and we have the ability to parallelize all those 100 across the available replicas, available image encoders, right? That's what optimizes TTFT in that, the image encoding time in that regard. And once image encoding is done here, it will relay back to the router saying, I'm done with encoding for the particular request, right? And then we update that request with statistics of where is the encoded token sitting, which of these replicas the encoded token sitting. And now that this request is ready to be routed to the text pool. And once this is received by the request router, that request will go to the text pool and will get routed. And when the text pool receives a particular request, it now has details of which of the image nodes has its tokens, right? So it will directly pull those tokens from the image nodes. And there are a lot of considerations done here with respect to why we came up with this architecture, right? A pool-based architecture rather than the image instances could have directly pushed to a certain text instance, right? Rather than going via this complicated route. And high level, the key reason why we did this is, one, if we look at the size of the image encoders versus LLM heads, these instances are always bound by memory capacity because these are large LLMs that we are hosting, whereas these are really small, few 100 million sized encoders that are sitting here, right? So there's a lot of spare memory on these replicas than here. So these tokens that we have embedded can sit on the image encoders until a point where they are needed by the text instances. So that's one of the key reasons why we ended up with this kind of a design, right? And then how does routing happen when a request comes into the image router? The idea we're using here is routed to the replica which has the least load at this point, and that in a way kind of balances the latency across all the available instance. And the same with text too. For decoder only models, you need to look at the combination of text and image because that's what's going to determine the load, and for cross attention models you can just look at text, right? And when it comes to evaluation, what this is showing is for different loads shown on the x-axis, how much does the throughput of the systems vary for a monolithic versus our system ModServe for the same number of replicas in use. And what we see is like a huge gain, mainly coming from the ability to parallelize a request across multiple encoders, right? And being able to do this parallelism independently for the encoders and the LLM head. Right? And this is also another interesting result, which is, as I said, the load could vary over time and you could have modality specific bursts, right? So the top graph here is showing what if you had a modality specific, like an image burst happening at one period of time. So what would happen in the monolithic case is that if you are auto scaling, right, you have a very good auto scaling feature in place, you will have to auto scale the entire monolith at this point, right? So the number of resources you need to scale is very high because the LLMs might need 8 GPUs and you'll have to scale this entire unit here. But then with ModServe, because you can independently auto scale, you could just auto scale the encoders, and because of that, the resource utilization at the peak is much, much better with ModServe when compared to this one, right? And you can see this difference is also higher for cross-attention models because the load here is higher, right? But here for the decoder only models, because the load on the text nodes will also increase whenever there's a modality increase, right? Because that will translate to text tokens. So because of that, the gap between ModServe and the baseline is kind of lower here, but there's higher savings in the cross-attention models.
The text one, right? So you're sort of basically assuming that these queries which are coming to mesh, they are like latency sensitive something, they are willing to wait.
Not really. So when we are doing the provisioning decisions or figuring out how many replicas we need, we make sure that that scheduling delay is incorporated in our P99 TTFTs when we are provisioning.
So in some sense, you're limited by.
Correct.
You have to provision it enough that image comes and all encoding it. So now think of image plus text as only as text, and you have to provision and show
Correct.
text.
Correct. Correct. Yes. Yes. Okay, any other questions until that point? I think I have just another slide on where the landscape is headed.
This encoding itself is a heaviest component.
Hmm.
Do you cache the encodings with the hope of future?
It is very unlikely because it's very unlikely for the exact same patch to repeat in a different image unless the same user is maybe sending in the same image for another time, right? Other than that, cross request, it is very unlikely. Although, like, I think at a production scale, we don't have this information too because we can't retrieve this information as to whether an image was repeated across users.
I think also is privacy.
Yeah. Yeah.
Who just should you know what I'm looking for?
But we do this in the text scenario, right? In the text scenario, cross users, we try to provide prefix hits. We try to cache in the hope that another user maybe asks a similar question, or another user could maybe retrieve the same document. So if you have preprocessed it, we cache it. But in the image scenario, the likelihood of such a cache hit happening is probably low.
Like especially in bursty scenario, suppose someone that someone looking for probably like
It could be the case, but yeah, we don't have data sets to validate that assumption too. It could be the case that maybe in an organization, everyone's trying to ask questions about the same video, right? In which case we could have the encodings cached. Yes, that is like probably a viable scenario. Yeah. Yes, you could cache it. Similar to how we do prefix caching, we could also cache images if they are repeatable. Mm-hmm. It is scheduling, but the reason I think deployment comes into picture is because we are moving away from silo and doing a different shared infrastructure itself, right? So from that point of view, not necessarily the same, right? Because the way you deploy will also dictate how many resources you do, how do you do capacity planning, all that will be kind of tied to what kind of deployment you do. Also because it ties with the title of the talk, yeah. Yeah. Okay. So at a high level, right, what are some emerging challenges in this space that we see? So I wanted to highlight like two emerging kind of trends that we're seeing, and a lot of interesting systems challenges could come up in this space, right? So the first one is RL post-training. So what do we mean by this? So previously we had just pre-train a model and then deploy it for a use case, right? But now you take this pre-trained model, you want to kind of align it with some user preference, or you want to align it with some particular use case. So you do RL based post training on this, right? And there are multiple steps in doing this, right? Which is you take the prompt from this smaller data set that you've curated, like a use case specific data set you've curated. And for this prompt, using the current model, you'll generate a bunch of possible responses for this prompt. So there is a inference phase that's happening during training, right? So during training, you kind of come up with new responses. And then what you do is you use a reward model to reward each of these responses. Okay, and then now you have an input prompt, you have the responses it generated and the rewards it gave. Now you do a backward pass over the model, current model, right? And you try to now align the model so that the next time such a same prompt comes in, it picks the response with the highest reward that was given, right? In some sense, you're trying to align the model to the new data set that you're trying to optimize it for in an RL based fashion. So the main systems challenge that comes here is that training also has an inference component here, right? And the way frameworks are today doing RL post training is that they'll use VLLM to do inference on a separate set of nodes, and then you'll do the actual back propagation on a different set of nodes, which is using maybe a Hugging Face transformer backend for doing the back propagation, right? So there could be a lot of opportunity here with respect to how resource utilization is, how do you efficiently do this entire post-training phase from a systems point of view. So that is like an interesting area that's coming up. And also because everyone is doing RL post-training now and models are having much better capabilities with post-training. So this is going to be a very widely used use case. But the other one I'm more excited about is agents, right? Like, what do agents mean? You want to completely automate end-to-end, development of something, And in the agentic scenario, you're going to have a lot of different models. It could be different or same models assuming different roles, talk to each other as well as talk to a bunch of tools that could be available. So there are a lot of distributed communications and interactions that are going to happen in an agentic setup. And some of the key challenges here are these agents or these models and tools are going to have variable resource needs. They are also going to have variable demands on memory and storage, right? Because in the context of simple requests, we used to think maybe another query will come in a minute later and use the KV cache, or that's why prefix caching works. But now with agents, I could come back tomorrow and say resume my session, or do something with the data that I was using yesterday, right? So the sessions could be persistent across days or across months. So does it make sense to keep redoing these computations, or what are the storage needs that this exerts on the system as a whole, right? So at a large scale infrastructure scale, this brings in a lot end-to-end latency. So there are a lot of challenges coming up in this, friends, and there are already interesting papers that are looking at the scheduling and the KV cache transfer aspects of it. And the other challenge that comes about is managing the distributed nature of these agents. Some of these agents could be on the edge, some of these could be on the server side, and how do you communicate between these agents? If you've heard of, there's like MCP and agent-to-agent protocols that are coming in, which defines how communication between agents happen, right? So what should that look like? So there are a lot of questions to be answered there. And then of course there are like privacy, security and reliability concerns, right? Privacy security of the data that's going from one agent to another, which could be hosted at completely different regions, different places, and also reliability, right? In this entire pipeline, even if one of them fails, how do you do failure handling? Do you restart the entire request? Do you retry at a particular request? How does this happen? Like, we've spent many years trying to do fault tolerance for training, right? And this is like an emerging use case where faults could happen anywhere. So how do we deal with those kind of scenarios? And the other thing, of course, this is getting more and more like a distributed system, right? So you need scalability, monitoring, figuring out the health of all of these. There are a lot of challenges that are coming up there too. So that way, I think the space is getting more and more interesting with respect to the systems challenges that it poses, right? That's kind of all I had. And if you want to learn more about the kind of work that we are doing in our group, our webpage has most up-to-date information on the kind of projects we are doing, some of our recent work if you're interested in looking at. And we are also always open to collaborating with students either as RFs or as interns. We've also had some RFs from IISc, master students from IISc who've come joined us and have continued to work with us as full-time employees. And we've also had PhD students come work with us as interns. If you're interested in this area, feel free to reach out and we can see. Yeah. Thank
Any
you.
questions? Thank you, Dr. Jayashree, for accepting our request and giving a wonderful talk. Thank you, everyone, for attending the talk, and have a great evening. There is coffee and other refreshments served in the coffee hut. Please help yourself. Yeah, continue your conversation.
Yes, yes.